All right, our group had 3 main points, and I actually have a few examples for some of these points. If I talk too much, tell me to stop, okay? All right, so our first main point here is amplification of nanomachine signal. And what that means is, well, from an end user standpoint, if we have to use an STM or SPM to see the output of our nanomachine or a single molecule analytical technique, that really makes nanomachines really difficult to use. We need nanomachines that are capable of routine and cheap readout. And so I can give 2 examples. First off is an ELISA, enzyme-linked immunosorbent assay. You can get incredibly low detection limits with an optical readout that can be, this can be performed in relatively primitive labs. And so the way this works, it's a chemical amplification of an optical signal. You have horseradish peroxidase that's tethered to your one of the final antibody, and you have an organic dye precursor that either has a signal that gets bleached or a signal that gets, or yeah, you're either you're changing an optical signal, you're bleaching something, or you're absorbing more. The other example I can give is qPCR. If I think of DNA polymerase as a DNA copy machine, well, with qPCR, as we make more of the defined length product, we get a greater optical signal. And this technique is so powerful. Yes, qPCR machines are more expensive, but it also has the capability of detecting a single sequence, a single copy of DNA, which is freaking incredible. I'll clean up my language. Yeah, like we really see amplification and nanomachine signal to be read out, by us at the macro scale to be a really big deal. Next up, we have close the feedback loop at the nanoscale. Oh boy, what does that mean? All right, so the macroscopic analogy I can think of is that, well, our complex machines that we use today, the different parts of the machine do not act independently. They interact with each other. And the one example I could think of is when we're driving a car and we turn, our wheels don't squeal because the inside wheels are turning less than the outside wheels because there's a differential. So the different parts of the car interact with each other. And I have 3 examples, 2 from nature, 1 synthetic. So the first example is, well, hemoglobin. So hemoglobin is not 4 separate independent oxygen binding centers. In hemoglobin, there's cooperativity between those bonding centers. When deoxyhemoglobin binds to that first O2, the entire conformation of the protein changes, and the affinity for oxygen of the remaining 3 sites greatly increases. All right, what this does is it changes a curve that would be like wide and shallow with 4 independent binding sites to more like a step function. And this is a big deal because it also works in reverse. When hemoglobin's in our blood and the oxygen concentration is lowering because cells are, it's being absorbed through the capillary walls or whatever, the hemoglobin releases that first oxygen, it changes the conformation of the other 3 subunits, and it dumps the remaining 3 oxygens. So the pickup and drop off of the oxygen is more of a step function. And this is a big deal. It's part of why we can efficiently use oxygen and be large. The next example I have is GFP chromophore. This is really, I find GFP so cool. The GFP chromophore is made of 3 amino acids. And if you look in all the other peptide sequences that have ever been determined and look for any examples of that chromophore in those sequences that contain those 3 amino acids, you won't find anything. And the reason why is because the GFP chromophore forces those amino acids to undergo a chemical reaction that would not otherwise occur were they not in the structure of the GFP chromophore. So think of a giant beta barrel, and it's like folding towards its thermodynamic minimum. And if the global minimum of the structure if the global large structure is tending toward a minimum, well, the part with those 3 amino acids, it's getting crunched. And those 3 amino acids are being pushed together such that they react with each other and form this chromophore. So this is an example of, if we thought of GFP as a signal reporter type machine. Well, when this machine creates itself, it forces part of it to create its function. The third example I can give, which is synthetic, would be, DNA tweezers. 2 sections, you have a binding sequence here. You can change the length of this sequence, and it's like a nutcracker. Right? So yes, think of a nutcracker, and the complementary sequence that binds these two ends, you can change that average distance so in the interest of time, the last one is controlled fabrication of color centers for optical magnetic resonance techniques. And this is a really big deal because, well, magnetic resonance, NMR, has absolutely revolutionized organic synthesis because it let us figure out what we were making. And it let us figure it out quickly and, well, with pretty high precision. And we don't have that at the nanoscale. But color centers in diamond, the NV center is the most famous. They can be optically, you can optically excite them. They luminesce, they do not bleach. And very, very importantly, that unpaired spin in that NV center interacts with other spins around it. And what you get is you get these off-resonance peaks that correspond to the frequencies of these other spins that are around the NV center. And this is a topic that I'm still learning about because many people want to do this, and I'm one of them. Because what this represents a tool that would let us do structural conformation at the nanoscale. And for us, for what we're doing, doing something like carbon-13 labeling, what we're doing so that we could see those carbons, or deuterium labeling of signals that we don't want, like deuterated solvent, and then looking at the protons around a center. Things like that. I'm saying this it potentially opens a lot of doors. NV centers are not the only color centers. It's my understanding that we're still discovering color centers in materials. And I will shut up now. Oh.
Any additions? No, you covered it. Thank you so much.
Could you describe the molecular tweezers a little bit more? It's kind of a cheating way to give you a little more time.
Awesome. Okay, so imagine my DNA strands, my arm is a DNA strand, and it's linked to another DNA strand. And at the ends of these strands, we have places where a consensus sequence combined and bridge them. And so you could have a long consensus sequence, and my arms are spread apart, a shorter consensus sequence, and my arms are closer together. And so if you're looking at a position like here-ish near my armpit or something, what you're doing is you're taking a large distance here, and like a lever, it's like a nutcracker. You're basically you're using a large distance change to create a much smaller distance change toward this hinge or fulcrum. Hinge, not fulcrum. Yes. And well, this is cool because I think we could use this to drive chemical reactions. If you could imagine two relatively unreactive in solution moieties in here, and suddenly we are moving them closer together. What are we doing? We're not lowering an activation barrier, we're increasing the attempt frequency for that reaction. And I find that really cool because what it does is it gives us control over the dynamics. It's DNA, it's in solution, it's doing this, but is it doing this or is it doing this? And that's something we can change. And that's fun. That gives us a possibility. And actually, it was pointed out to me that would be a relatively easy thing to confirm because it's just, if that reaction occurs, you've just ligated those strands together. You can run a gel and be like, hey, this band, well, if you do it on ensemble and you have enough to run a gel, you could see it. And so I think of this as very much like an analog engineering idea. The device, the structure of the device has to be the thing that transduces the signal to the other part of the device. And that's what I was getting at with these examples with, the big one being hemoglobin, that those subunits are not independent of each other. Their behavior is coupled. Yeah.
Thank you. Awesome.